So once you have like a 3D picture of it, then the next step is to evaluate its polarity. And we do that so we can get an idea of the overall polarity of the molecule, to know if it's going to be water soluble or fat soluble. And our next thing that we'll talk about after covalent bonds is intermolecular forces, which is like how things dissolve and how they behave based on if it's polar or not. So then this next step here we'll call assessing polarity. So for polarity, what that means is is the molecule polar? We call it is the molecule polar. So for this, first we need to identify any polar bonds. And any polar bonds are going to have an electronegativity difference greater than or equal to 0.5. But also less than 2.0. And that electronegativity value is given for each of our atoms. And it's something that there's like a couple of different evaluations of it. It's a measured value that's reported. And I give you like a chart for it that we'll use, right? And it's like, there are others that are slightly different, but like, let's just use the same one. So for hydrogen, it has an electronegativity equal to 2.1 about. Nitrogen has an electronegativity equal to 3.0, and oxygen has an electronegativity equal to 3.5. These electronegativity values are going to be on a scale of 0 to 4, and fluorine is going to be something that has a 4. So it's going to be our most electronegative. And this is really about how good is that atom at attracting electrons to it, essentially. It's like how attracted to the atom or to the nucleus. It's like how electron greedy are they? Like how much do they hold on to them and not share? And this is really just going to be looking at uneven sharing of electrons. So what we do once we have our electronegativities of our atoms is we look at each of our bonds. And so we have nitrogen and hydrogen bonds. We have nitrogen and oxygen, and we have oxygen and hydrogen bonds in our molecule. And so we're going to subtract, we're going to look at the difference of our electronegativity values between those two atoms for each one. So nitrogen is 3.0, and so I would subtract the 2.1 of the hydrogen. So that's going to give me a value of 0.9. And so that's equal to our difference in our electronegativities. For our nitrogen and oxygen, it's 3.5 minus 3.0. So that's equal to 0.5 for our difference in electronegativity. And our oxygen hydrogen bond is 3.5 minus 2.1. That one's kind of big. So that's going to be 1.4 for our difference in electronegativity. And so all of these are greater than or equal to 0.5, right? Therefore, they're all polar. So all of our bonds in our molecule were polar this time. It doesn't always happen. So I'm going to identify that in a couple of different ways. Here, I'll draw it right here on the side. So one way to do this is to use delta positive and negative symbols. So if we have a bond that's like, if I put a delta negative versus a delta positive, this means partially positive and partially negative. Really means that this X is has the shared electrons are around the X more. You could like draw the like electron cloud would look like this probably. And so it's just going to have more time that it's around the nitrogen. Another way you could draw it too, that I kind of prefer, you could also use an arrow like this, where the plus part of the arrow is pointing towards the partially positive side, and the arrow points to the more partially negative side. It means that the arrow is going to point to the more electronegative element. So let's go ahead and do it with the arrow, and then we can do it with the delta symbols too. So all of these were polar. So all of these bonds are going to get a symbol. If it was a non-polar bond, if it was less than 0.5, you wouldn't draw anything, right? Because we're just worried about identifying these polar ones. If it's non-polar, just like we don't draw anything to indicate that. So my hydrogen was less electronegative than my oxygen. So I'm going to have the plus end of the arrow by the hydrogen, and it's going to point at the oxygen. My nitrogen was less electronegative than my oxygen, so I'll have it point to the oxygen again. And my my nitrogen hydrogen bonds, the hydrogens were less electronegative and the nitrogen was more, so my arrows will point to that. So now I've identified all of my polar bonds. And I'll show you how else you can draw it. Okay. The other way to do this is to put, for this bond right here, this was the partially positive and the nitrogen's partially negative, and the hydrogen's partially positive. Now it kind of switches because here the nitrogen's partially positive and my oxygen is partially negative. And between the oxygen, hydrogen, the oxygen's partially negative and the hydrogen's partially positive. For these ones, it's you got to be careful. It's not across the whole molecule. It's only on the bond. So these delta plus, delta minus need to be on either side of the bond. All right, so the second step after you identify them all is decide if the molecule is overall polar. So in general, if there are polar bonds, then you can say it's a polar molecule. Except if there are no lone pairs and all of the dipole moments like cancel each other out, like they're all pointing in opposite but equal directions. So in this case, our molecule has lone pairs. So it's going to be overall polar. So let's say NO. So it has lone pairs, all bonds are polar. Therefore, it's polar. To decide like what its overall dipole moment is, you take the average of all of those little dipoles on your bonds, and you try to think about like what is its overall direction. So like this is like essentially vector math in your head, which is either easy or hard depending on like how you process information. So let's get this wider. So in general, I had the dipoles pointing from the hydrogen to the nitrogen and the nitrogen to the oxygen. So I can kind of like take the average of those and say, well, these ones were kind of going in this direction. Plus I have a little bit kind of going up and over. So I'd say overall, this one is going to go a little bit like this. Or maybe actually like a little bit pointed towards the oxygen, like that. And so we would call this our overall dipole moment ish. And it's hard to get exact, and you're not going to be graded on the exact like way it's pointing. So an example of something that wouldn't be polar. So let's say like polar bonds, but overall non-polar. It'd be like this. So here we have all of these are polar bonds between the carbon and the fluorine, and there's no lone pairs, and they're all pointing opposite and equal ways away. So these are all going to cancel out. So like if you added up all those little vectors, it would equal 0. So those are kind of the cases where that happens. It's not like super common, but it happens, especially with these small molecules. All right.